All right, chemists, in our last lesson, we introduced the concept of equilibrium and looked at expressions for the equilibrium constant. Today we're going to combine this with what we know about simple stoichiometry and look at how we can use aspects of stoichiometry and the equilibrium constant to quantify things about equilibrium reactions. Since equilibria processes don't go to completion, we can't just use our regular old 1 mole of something becomes 1 mole of each product, although those ratios we'll see are still important. I'll show you a couple of different ways to do this, and we're just going to dive right into a problem. Many folks call these rice chart problems because it's just a way of tabulating the stoichiometry, but all we're doing is tracking the stoichiometry. The first one sets up a way of giving us initial concentrations of a process, and it wants us to figure out what the equilibrium constant is. It says we have some amount of phosphorus trichloride and some amount of phosphorus pentachloride, which are one of the products and the only reactant in an equilibrium reaction. And then they know how much of the other product is found once it equilibrates, which is not completion, but a dynamic, steady state process where we're no longer changing the amounts of things. The term rice is just an acronym to help us remember what we have to do. It starts by just writing the reaction. So I'm just going to rewrite the reaction. Phosphorus pentachloride reversibly becomes phosphorus trichloride and a chlorine molecule. And it says I, meaning initial. What are the initial amounts of each thing? Well, they tell us there's 0.298 moles of PCl3, so I'll write that just below the PCl3, and there's 0.00870 moles of PCl5, so I'll similarly write that below the PCl5. By virtue of the fact that it doesn't mention Cl2 in the beginning, it does mention how much we have at the end, I'm going to put a 0 for the Cl2. Now this will react. This reversible reaction is not currently at equilibrium. Remember in the previous lesson we looked at calculating Q. We could actually do that right here. Q is the same expression, it's reactants over products. Well, one of my reactants is currently 0, so Q is actually 0 right now. That means that compared with K, which is never a negative number, K is greater than Q. So this reaction is running forward. Remember that greater than symbol points to the right in this case. That makes sense conceptually. We have no chlorine yet, so of course the reaction is running forward. We're going to make some chlorine. I don't know how much we're going to make, but let's give it a variable, and I know for however much chlorine I make, I'm going to lose that much PCl5, and I'm going to gain that much PCl3. So I'm going to write minus X for the PCl5, and then plus X for the PCl3, and also plus X for the chlorine. That X is an unknown right now. We'll see it's actually very easy to get for this problem, but I'm just going to leave it as a variable because we'll use this again later. And it gives us variables that are related to each other for the equilibrium amounts of things. 0.00870 minus X for the PCl5, 0.298 plus X for the PCl3, and then just X for Cl2. So I can write my equilibrium constant, and I'm going to write it in terms of concentration. They're asking for concentration, so I'll use Kc. That's easy. It's all in 1 liter. So actually these moles are the same as molarity because the volume is 1. Nonetheless, I'll write the expression first. It's bracket PCl3 raised to the first power times Cl2 raised to the first power all over PCl5 to the first power. And I can now substitute my expressions with my X terms. My PCl3 is 0.298 plus X, chlorine is just X, and my PCl5 is 0.00870 minus X. And I'm looking to figure out what K is, although hang on, I actually know what X is. X was given in the very beginning of the problem. X is 0.0020 because it says that's how much is at equilibrium. So X is 0.0020. 200 because they just told me that. So I simply have to plug this value of x into all these different expressions and do the math. We can do that separately on your calculator. When you do that, you get 0.0896. So this was a case of just incorporating the stoichiometric changes that happen. Notice those x's are in a 1:1:1 ratio because the coefficients are 1, so they still react in mole ratios. We just don't go to completion in this case. We don't consume all of the PCl5. There's going to be some of everything because this is a reaction that exists in an equilibrium, a significant equilibrium. Okay, let's take a look at a few others and change the question a little bit. This time, we're actually given the value of K and initial concentrations. I want to know how much of everything is present once it equilibrates. Different reaction, new K value, and different pieces of information. Let's start the same way. Let's just write the reaction. This is 2NOCl, reversibly forms 2 nitric oxides, and a chlorine. And I'll scan the problem. All they tell me is that the molarity is 0.5. So I'll say 0.5 for the NaOCl, and I'll infer that that implies 0 for the two products. Now, notice in the first example, I was using moles, and in this example, I'm using molarity. Is it okay to use both? Well, the answer to that for now is yes, as long as everything is in the same volume. Remember, we describe who's a reactant and who's a product. These are just dumb old molecules in some reaction flask, and they don't know who's who. We have NOCl and NO and Cl2 all combined in some space. So if you're in the same volume, you can use molarity to molarity ratios the same way you would use mole to mole ratios. It's kind of like how last semester we used atmosphere to atmosphere ratios as well when you're talking about gases. We'll see that sometimes that's not true if you have to combine two separate volumes into one big volume, but that's not what's happening here. This is all in one space. It's a gas phase reaction. Anyway, let's fill in the change row. We can tell which way this is going. We have no products, only reactants, so it's clearly going to go forward. So my terms of x are going to be 2x of the NOCl, 2x of the NO, and x for the Cl2. That's just the coefficients becoming the factors of each x. And since it's going forward, we're going to lose 2x of the NOCl and gain 2x of the NO and Cl2 product. So at equilibrium, I have 0.50 minus 2x for NOCl, 2x for nitric oxide, and once again x for chlorine. Now, they actually give us the numerical value of K, but I'm going to first just write the expression. I'm going to write it in terms of the x's. We know it's nitric oxide squared times chlorine to the first divided by nitrosyl chloride to the second power. Let's substitute in what we just wrote for x. That's the quantity 2x squared times x divided by 0.50 minus x squared. And I could, if I wanted to, expand this. I would get a cubic expression, a very complicated cubic expression once I combine like terms. And I could solve for x, but the AP never wants you to have to do that. We're going to think first and then do the math. So think, then math. That's what chemistry is. Chemistry is math with a lot of thinking first. That's just what we run into. So let's think. The K value for this reaction is very small, 1.6 times 10 to the negative 5. So K is small. And therefore, that means that when this thing hits equilibrium, it's mostly reactant heavy. It's mostly going to be what's in the denominator of that expression. That's what a small K value means. It's going to be mostly this stuff. So I don't know how much of the NOCl is going to get lost, but it's probably going to be pretty negligible compared to how much I'm left with. I'm not going to lose 0 of it, but I'm going to lose very little compared to what I started with. So we are going to assume, mathematically, that whatever 2x is, it's much less than the 0.50 that we started with, which means I can simplify this expression by changing the denominator to just getting rid of that minus x term, and it becomes the quantity 0.5 squared. I'm not saying x is 0. This does not mean x is 0. This just means that however much I lose is negligible compared to the 0.5. So it's 0 compared to 0.5, but the difference is negligible. And now I have a very simple cubic expression that I can solve. We're given the value of k. It is that small number, 1.6 times 10 to the minus 5. And if I simplify this expression up here, I get 4x cubed all over 0.25. And that's such a simple cubic. You can actually do this without even a calculator if you watch, just by coincidence of the numbers. 1.6 times 10 to the negative 5 is the same as 16 times 10 to the negative 6, because 1.6 is 16 times 10 to the negative 1. And 0.25 is a fourth, so if I multiply both sides by a fourth, I get 4x cubed is equal to 4 times 10 to the negative 6. And you can divide both sides by 4, and then x is simply the cube root of 10 to the negative 6, which is 10 to the negative 2. Not only was it an easier cubic to solve, I could do it freehand without a calculator, just luckily because the numbers were so nice. That would not be the case if I went back and solved this cubic. Again, you could do that. You could expand it and solve that cubic, but we're not expected to at this stage of the class. We haven't actually finished answering the question. The question wants the equilibrium concentrations of everything, and x is just what the Cl2 is equal to. I want these other two things as well, so I'm going to write those down below. It's concentrations. Remember, these already are concentrations, because we started with using concentrations. So the molarity of NaCl, which is 0.5 minus 2 times x, is actually 0.48 molar now when you subtract 2 times 0.01. The molarity of NO is 2 times x, which is 0.020 molar. And the molarity of Cl2 is just x, which is 0.010 molar. And there's our x values plugged in to give us our concentrations at equilibrium. At equilibrium. Now it's fair to say, and it's fair to pause and go back for a second and go, when can we do this assumption? When is k small enough? I just sort of arbitrarily said, oh, it's small. Well, what constitutes small? We are going to check the percent dissociation. So when is this okay? Reminding you that, like this shortcut, we have to check the percent dissociation in order to do that. We'll often find that for most of our problems, it's pretty intuitive when you do enough of them that it's going to be okay a lot. But I'll prove to you that it's okay because chemists have declared that if the percent dissociation, which is equal to whatever you solve for as x, divided by your original amount, NaCl, and multiply that by 100, if that's less than 5%, we've deemed that to be okay. In other words, is this difference 5%? Oh, whoops, I actually made a mistake up here, didn't I? This should be 0.5 minus 2x. 0.5 minus 2x, just squeeze that in right there. Which really means the percent dissociation is how much of that we lost. In this case, that actually means it's 2x, isn't it? So what we solved for x was 0.01, and our initial NaCl value was 0.50. Multiply that by 100. When you do that, you get 4%, which is less than 5, and chemists have said that as long as it's less than 5% dissociated, as long as that difference is within 5% of what we're losing it from, that's okay. So this one is actually pretty close to being not okay. Makes sense when we plug it back in, you actually get a difference that's measurable, but it's close enough. You want to prove it to yourself? Go back and solve the actual cubic without that simplification. You'll get numbers that are very close to these. In fact, if you follow sig fig rules, you might get exactly those numbers. Okay, there's one left, and I want you to hit pause and see if you can try this one, or at least set up the first 2 or 3 rows of this. Here's a new reaction, different K value. This time K is not small, and you'll see we can't use the shortcut that we just used, but we can still solve it without having to solve a complicated cubic. Hit pause and see if you can set up the first 3 rows of the Rice chart, given the information in the problem. Okay, let's see how you did. So the first thing is just to write the reaction, hydrogen plus fluorine reversibly forms 2 equivalents of HF. They're giving me molarities. I'm going to assume this is one big gas phase reaction, so I'm going to just use molarities. So I have 1 for the hydrogen, 2 for the fluorine, and 0 for the HF initially. We are going to go forward once again because we have no product, so the reactants are going to react. I'm going to lose some X, I'm going to lose some fluorine, I'm going to gain 2X of the hydrofluoric acid, or actually hydrogen fluoride, because it's in the gas phase. So at equilibrium, I have 1 minus X, 2 minus X, and 2X for the HF. So hopefully you were able to get at least that far. Now let's write out the K expression. K, in terms of X, is equal to 2X squared divided by 1 minus X times 2 minus X. K is not small. K is appreciably 115. So I have to actually solve a quadratic here. So we're going to expand this. That becomes 4x squared in the numerator, and it becomes 2 minus 3x plus x squared in the denominator. And that's all equal to 115 because they gave us the value of K. I know what K is. It's 115. So now let me cross multiply and show solving the quadratic. 115 times 2 minus 3x plus x squared is equal to 4x squared. Let's distribute and combine like terms, which really just means combining the x squareds, and set it equal to 0. When I do that, I get 111x squared minus 345x plus 230 when I write it as an x squared plus bx plus c equal to 0 expression in your classic quadratic. And I'm just going to write the word quadratic, meaning I went ahead to a quadratic solver and didn't do it manually. And I come out with 2 solutions. It's either 2.14 or 0.968. And if we stop in the mathematics department, we'll go, yep, there's 2 solutions. But we're chemists. We have to think. We have to think. We can't have 2 answers in this case. There must be only 1 solution. Well, look at what x is. X is never any of the actual amounts. X we either have to double or subtract from given values. We can't subtract more than what we have in the beginning. So this first answer cannot make sense conceptually, which means we actually are stuck with our final answer, just with a little bit of thinking. And when you plug x back in, you get a value for hydrogen, which is 1 minus x, so 0.032 molar. A value for fluorine, which is 2 minus x, that's just 1.032 molar. And then a value of HF, which is 2 times x, and that's 1.94 molar. And those are the amounts that we would expect at equilibrium. You can even do a little self-check and make sense of it. K is an appreciably large number. It's 10 to the 2. So it's mostly product. A little bit more than the amounts of reactants. Not a huge amount more, but a little bit more of product because K is big. In fact, you could do the same thing with the previous question. K was really small in the previous question, so we are mostly on the reactant side, not a lot of products by comparison. So that's how you use Rice charts, what are called Rice charts, to solve equilibrium problems. All we're really doing is tracking the stoichiometry, keeping in mind that none of these actually go to completion. We can take some mathematical shortcuts to help solve more complicated cubics based on the magnitude of k value, or if necessary, we can actually solve things like quadratics. I'm never going to make you solve a cubic, but you might need to solve a quadratic going forward. And that's how you deal with race charts.